So in this lesson, we're going to talk about deformation of rock. And deformation of rock is quite simply any change in the shape or size of a rock. What we're talking about is forces, which we'll call stress, leading to strain, which is this deformation. Now, things that are going to affect deformation will be like temperature, pressure, rock type, and time. Now, temperature and pressure we've talked about before. If we put rocks under great pressure, if we put them under great temperature, then those rocks can change, and that would be metamorphosizing the rocks. But they can also cause them to change their shape or their size, and that's where we have deformation. So, temperature and pressure can cause either metamorphosis or this deformation of a rock. Now, the rock type. Some rocks are going to be more apt to this deformation, and some types of rocks are going to prevent this deformation, so to speak. It's going to be harder for them to change the size or change the shape of the rock. And then finally, we have time. If we apply a smaller amount of pressure over a long period of time, we can see deformation. Or if we have a really strong pressure, it might not take as much time. But if we have this long period of time that we do in Earth's history, then it gives us the ability that we can then cause this deformation to happen. Now, when we're talking about deformation, there's two different kinds I want you to be familiar with. We have brittle deformation and ductile deformation. Brittle deformation is where it'll break, where the rock gets to be very brittle, it breaks into smaller pieces. Ductile deformation is a little different. That's where it's going to change shape. It's kind of like if you put a penny on a railroad track. If you run over it with the train, it doesn't break, but it changes its shape. It just kind of gets flattened out a little bit. Okay, so let's examine the types of stress. These are going to be the forces that rocks are undergoing inside the earth that causes this deformation. The first is tensional stress, and tensional stress is where we have a rock being pulled apart. And you can see the arrows here, and you can see the stretching out of the rock, and that's what tensional is going to be. We can have the opposite of that, which we call compressional stress. And compressional stress is where we're going to apply a force squeezing that rock together. So we're compressing it. And then the third type of force is what we call shear stress. And shear stress is where we have these forces acting in opposite directions. And you can see how it's kind of bending and twisting that block. So these are our three different types of stresses. We have tensional, compressional, and shear stress. Okay, the last concept they're going to cover in this unit is isostasy. And isostasy is this concept of a floating crust and gravitational balance. And what we're talking about is if we look at our picture here, we'll notice that originally we had this tall mountain. And as we have this tall mountain, it's going to have more crustal material. It's actually going to force its way down. It's going to be heavier. It's going to cause it to sink a little bit more into the asthenosphere. So it's going to force this down a little bit. As we have erosion, and you can see this erosion coming and taking away this top part of the mountain, that's going to cause it to be a little bit lighter, and you're going to have this uplift occurring, and it's going to kind of move upwards a little bit. So it's isostasy says that these big pieces of our crustal plates, they're going to kind of go up and down depending on the amount of stuff that's on there. So the heavier plates are going to sink a little bit more. As they erode, they might rise up a little bit, and it doesn't have to be the whole plate. It can just be parts of the plate that this is happening to. Okay, well that's it for our video. As always, good luck in the lessons and the quizzes, and we'll see you in the next video. Okay, a little bit later on in this course, we're going to discover that sedimentary rocks like to lay down in layers horizontally. And when they're undisturbed, that's how they're going to remain. But when we apply forces, we can cause these layers to become disturbed, and they no longer have that flat look. They kind of get buckled. It's kind of like if you took a piece of paper and you pushed the edges of the paper together, it would kind of bump up like that. And that's what we notice happens with these rocks. When we call these rocks, when they're doing this, we call this a fold. Now, two types of the folds that we're going to talk about are an anticline and a syncline. Anticlines are folds where it kind of curves upwards. Synclines are the opposite. That's where it curves and comes downwards. And normally these are going to be in conjunction with each other. That means we'll see anticlines and synclines. And you can see how it lines up if we look. We have an anticline, a syncline, anticline, syncline. The third type of fold is what we call a monocline. And a monocline is kind of where we have a little step. So if we look here, we can see how it kind of goes and it steps down like that. And that's what a monocline is. So it's not a curve upward, it's not a curve downward, it's just kind of like a little step. And that would make it a monocline fold. Okay, so when we apply these forces to these rock layers and to these plates, occasionally they break. And when they break, we call that a fault. And there's several different kinds of faults, and we're going to go through those real quickly. The first one is what we call a normal fault, and it's caused by tensional forces. And if you can recall, tensional forces are going to kind of stretch this apart. So as that happens and we break here, you'll see that the hanging wall is going to slip down primarily off the footwall. We're kind of pulling it apart, and that allows it to slip down a little bit. And that would be a normal fault. Okay, and the opposite of a normal fault is what we call a reverse fault. A reverse fault comes from compressional forces, and that's where we're going to be squeezing these rocks together. And as we do so and we get a break, then we can see that this hanging wall is going to be thrust up and over the footwall. So it's the opposite motion, and that's because instead of pulling them apart like we did in a normal fault, we're squishing them together in a reverse fault. Now the angle of the fault is really kind of important. If it's a steep fault, we call it a reverse fault. If it is a shallow or almost horizontal one, then we call it a thrust fault. A thrust fault also has these compressional forces, so it's being squished together, but here you can see that the fault is going to be a very shallow angle, and because of that we call it a thrust fault. And finally, we have a strike slip fault, and this is caused by shear forces. And you can see how the upper block is going to be thrust this way, the lower block is going to go the other way. And now notice that we don't have any going up and over like we did in the other faults. These are kind of more side-to-side faults. And these ones here is where you would see, like if we had a road, the road would be here and it would show up here, and you'd see how it was shifted over when we had that earthquake. Now, if we have a lot of these compressional forces going on here, what we can do is we can build up a bunch of folds over time, and that'll get us folded mountains. And folded mountains, if you looked at the rock layers, you would see that we would have these folds inside. And you can see an anticline and a syncline over here. And you're just seeing it's basically if we took this mass of continental crust and squished it in together, that it would buckle and fold, and that's what would give us our folded mountains. Okay, just like if we have excessive compressional, we can also have excessive tensional stresses on this crustal mass. And as that happens, you'll notice we're pulling it apart here, and that's going to cause an awful lot of faults going on down here. And that'll cause it to break, and we end up with these blocks, and that's why we'll call them a fault block mountain system. Now, a couple terms you want to be familiar with in the fault block mountains. We have the horst, which is the upper part of the mountain, followed by a little basin looking thingy like a graben there, and these are going to run parallel. Okay, so this is when we talk about basin and range area. Here we have our ranges, and then we'll have our basins as well. Now, some other formations that can be caused by these internal forces would be like a plateau, and that's where we have a high elevation level surface. That means that the whole area was just lifted up. We can also have a dome, which we're going to see an upwarped angle, and you can see that down here where we're seeing this upwarping, and that's going to form a little bit of a dome. Generally, they're going to be circular. We can also have a basin, which is where it's going to be coming down and squished like that, and you can see that they can be quite large, but they're going to have that circular shape as well. Okay, well, the lesson will go into a lot more detail than I did here. I just wanted to introduce it to you. Good luck on your lesson and your quiz, and we will see you in the next video. So the first type of boundary we'll talk about is this ocean-to-ocean convergent boundary. Now remember, that's going to be oceanic crust with oceanic crust, and we're going to have this subduction. And as this oceanic crust is being subducted, we're going to see this melting. That's going to cause magma formation, which is going to rise up to the surface, and we're forming these volcanic island arcs. So we'll see mountains, but they'll be volcanic mountains in nature. And this is the first type of boundary. We can also have ocean continental convergent boundaries, and this one we'll see this oceanic crust, but this time it's a continental crust that it's going to collide with. And as it does so, we see the subduction, we see the melting again, but instead of forming a oceanic arc, we're going to form a continental volcanic arc. So we're going to see more volcanic activity this way as well. Now, we would kind of think that if we're seeing this convergent boundary, we're going to be talking about subduction, we're going to be talking about volcanic activity. But when we have a continental convergent boundary, then it's kind of more like a car wreck. And if you ever looked at the hoods of a car when they collide, they kind of buckle up, and that's what we kind of see going on here. We have one continental plate going this way, the other one coming this way, and they're going to collide and form this big mountain range here. Now, the best example of this is if we have the Asia plate and the India plate, then we're seeing this occur currently, and we form the Himalayan mountains, including like Mount Everest. And India is still moving, so Mount Everest is still growing. So we don't have volcanic activity, but we still have mountain building activity on a convergent boundary. So that's our convergent boundaries. What if we have a divergent boundary? Well, we talked about divergent boundaries, and we said that the plates are moving away from each other, creating this gap, and we call that gap a rift valley. In that gap is where we're going to see magma rise up, and we'll see volcanic activity going this way. So in Africa, there's a rift valley, and that's where we have some volcanoes like Mount Kilimanjaro that are forming. This is also how we form our mid-oceanic ridges. So that kind of explains our boundaries. Most of the boundaries are going to have volcanic activity, but when we do have the continental, we'll still get mountain building without that volcanic mountain building process. Now, one of the terms that you're going to hear about is accretion. And accretion is where we're adding bits, pieces, and things of that nature from one plate to a different plate to build it up. And if we look down here, we can see that we have an island arc, and I'll show you how that's going to collide in here. But we also have these displaced continental fragments, and what that is that's what we're talking about, is this accretion, is they're just kind of adding up to that. So let's take a look at what that really looks like. Now in this picture, what we're seeing is a continental landmass and an oceanic landmass in a convergent boundary. And you can see that there's this inactive volcanic island arch here, and as this oceanic plate is subducting and moving towards the continental plate, we'll see that this island arc is also going to be moving in, and ultimately it'll fill in where the trench is, but we can also see some mountain building over here where it does actually have that collision. So these islands are going to break off, fill in the trench, and start adding to that accretion, adding to that new material to the continental plate. Okay, well, that's the introduction for this unit. As always, they'll give you more information in the lessons. Good luck with the lessons and the quizzes, and we'll see you in the next video.